Okay, so today we will solve some end of the chapter problems in chapter 5. Once again, I have divided this up into two parts just to break up the sections a little bit. So in the first part, we will cover primarily covalent bonding, Lewis structures of molecular compounds and polyatomic ions, valence electrons, covalent bonds, and also talk about how to systematically draw Lewis structures for such compounds. Okay, so let's look at some problems from the chapter. Starting with something very simple, how do you distinguish between ionic and covalent compounds, ionic and molecular compounds? So which member of each of the following pairs of compounds would most likely contain covalent bonds? So you need to remember that a bond between cation and anions is an ionic bond, and metals make a cation. Of course, ammonium is a very prominent polyatomic cation that also makes ionic compounds, but it is not, does not have a metal. So, keeping that in mind, in general, ionic compounds, are made when metals combine with non-metals. And I say in general because one notable exception would be ammonium. Ammonium, NH4 plus, is an ion, makes ionic compounds, but does not have a metal in it. So you do have to be aware of that. So in general, yes, ionic compounds are metal plus non-metals, with the exception of ammonium. And molecular compounds, or let me change that, whereas covalent compounds or covalent bonds are made when non-metals combine with other non-metals. So please do remember, I have said this a couple of times already, but I'll say it one more time, ammonium is something that you do have to watch out for. Okay, so first is barium oxide or carbon or CO. Now barium is a metal in group 2A, an alkaline earth metal. So this compound has to have an ionic bond, which leaves us with this compound CO with a covalent bond, because carbon is a non-metal, as is oxygen. Using the same logic, ClF or NaF, Na is a metal, but Cl and F in this compound are both non-metals, so this is the one. FeCl3, I seem to be missing a compound there. FeCl3 and NCl3, that's the one I'm missing. It has to be, just one second, what happened? Oh, there we go, sorry. Or NCl3, I'm missing that. So yes, same logic, metal plus non-metal is ionic, but non-metal and non-metal are covalent, so that is covalent, and in the next case, CH4 will be covalent. Draw Lewis structures to illustrate the covalent bonding in the following diatomic molecules. Now, this is a simple Lewis structure without using all the steps and procedures. All we have to do is look at each element and its valence electrons. So hydrogen has one valence electron, and iodine, belonging in the group 7A of the periodic table, has 7 valence electrons. So if they decide to share their electrons so as to make a compound, they pool in other words, H and I. There is one pair of shared electrons, and then iodine also retains to its 3 non-bonded pairs of electrons. So in this case, the Lewis dot structure will be Hi with 6 valence electrons to it. IBR, once again, the same process. It's always a good idea to start with the valence electrons on each of the atoms. Iodine, group 7A, 7 valence electrons. Bromine, also group 7A, and hence also 7 valence electrons. They share 1 electron each and make a bond between the two. Remember, 1 bond equals 2 electrons. Each of these little lines that you see connecting atoms, each of these is a bond. It's a covalent bond, I should say, covalent bond, and each of the covalent bond equals 2 electrons. It's always an electron pair. So that would be IBR. Okay, how many non-bonding electron pairs are present in each of the following Lewis structures? So all we have to distinguish here are the shared electron pairs from non-bonding electron pairs. So non-bonded electron pairs are those that only belong to one single atom and are not shared by 2 different atoms. In this case, the non-bonded electrons, this is one on, this 1, 2, 3, 4, 5, 6, 7, and 8, right there. Those are not being shared. Those belong to individual atoms only. So the question just says how many. So there are 8 pairs of non-bonded electrons in this case. Going on to the next example, same idea. The shared ones are bonded. Those are the ones that are making the covalent bond. So we are looking at the unshared. 1, 2, 3, 4, 5, 6. And that's it, 6 pairs of non-bonded electrons. Okay, let's move on. Specify the number of single, double, or triple covalent bonds in each of these. Now, please remember, one covalent bond equals 2 electrons. So a double bond, which means there are 2, oops, I forgot, bond. So if there are 2 bonds between 2 atoms, which is a double bond, that's would have 4 electrons or 2 pairs of electrons. A triple bond, which is really just 3 covalent bonds between 2 atoms, will then be equal to 6 electrons or 3 pairs. So one covalent bond is 1 pair of electrons being shared. Double bond is 2 pairs of electrons being shared. Triple is 3 pairs. So let's look at this. Now, for the first example, those are non-bonded because these electrons are not being shared by the 2 atoms. So we should not be looking at them. But if you look at the electrons in the middle of the 2 atoms, there are 6 of those, which means 3 pairs of electrons are being shared, which then implies that it's a triple bond between the 2 nitrogen atoms. Now, in this case, here is one shared pair of electrons between H and O. Here is another one. And so since each pair of atoms is sharing only 1 pair of electrons, each of those, therefore, are single bonds, and there are 3 of the single bonds in this case. So there's 1 triple bond here, but there are 3 single bonds here. That doesn't look very nice. Let me write it again. 1 triple bond. Okay, so now here's a single bond, but that is a double bond. So in this case, there are 2 single covalent bonds and 1 double covalent bond. So one more time, single, 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 but this one right here is a double. So this one has 4 single covalent bonds and 1 double covalent bond between the 2 carbon atoms. Okay. Next question. Convert each of the Lewis structures in the previous problem into the form in which lines are used to denote shared pairs of electrons, including non-bonded electron pairs. Okay, so once again, remember that 6 electrons being shared, 3 pairs being shared implies a triple bond between the 2 nitrogen atoms, and then the unshared electrons stay with each of the atoms that they're associated with. So that's for N2, nitrogen gas. Hydrogen peroxide, once again, there is a single bond between H and O, there is an OH, single bonds. Oxygen has 2 lone pairs. This oxygen also has a lone pair. I just noticed that I did make a mistake. Hydrogen shouldn't have that electron pair. Just a second, I probably made that mistake in the previous example as well then. Hydrogen shouldn't have that electron pair. Hydrogen only has 1 valence electron, so it cannot have more than helium's electronic configuration. Okay, so that is hydrogen peroxide. This one, hydrogen, single bond to carbon, single bond to the second hydrogen, double bond to the oxygen, and in addition, oxygen has 2 lone pairs. Here, hydrogen, single bond carbon, double bond carbon, single bond hydrogen, single bond, and single bond. So once again, please remember, each of these lines indicates a covalent bond, and each covalent bond is 2 electrons or 1 pair of electrons. Okay, moving on. Sorry. Indicate whether each of the following is or is not a normally expected bonding pattern for the element shown. Now, in this question, what you need to remember is that the number of covalent bonds that a non-metallic atom would make equals number of electrons needed. Let me rewrite. Okay, number of additional electrons needed to make octet, to follow the octet rule. In other words, we need to see how many valence electrons each of these atoms has, and therefore how many more do they need in order to complete their octet, and that will equal the number of valence electrons, number of bonds, covalent bonds the atom needs to make. So if you keep that in mind, oxygen has 6 valence electrons. In other words, it needs 2 more electrons to complete the octet. If it needs 2 more electrons to complete the octet, which basically means oxygen atom must make 2 covalent bonds. Now, these 2 covalent bonds can be in any form. In other words, these can be a double bond. That's 2 covalent bonds. Or it could also be 2 single bonds and would also then satisfy its octet. So this is basically what you need to remember in order to answer this question. So let's answer it. So do you think A is normal? Yes, it is normal because oxygen must make 2 covalent bonds. In this case, it's making 2 single bonds and therefore now has an octet. This second one is normal as well because nitrogen has 5 valence electrons. In other words, it needs 3 more to complete an octet and hence must make 3 covalent bonds. This second, part D or C, it should be C, is not normal because carbon has 4 valence electrons. In other words, it should make 4 covalent bonds. So that is not normal. And D is normal as well because oxygen is making 2 covalent bonds, which is the number of electrons it needs, number of additional electrons it needs to complete the octet. Okay, so identify the period 2 non-metal that would normally be expected to exhibit each of the following bonding capabilities. Again, this question uses exactly the same idea, which is that the number of covalent bonds non-metallic atom would make equals the number of additional electrons it needs to complete its octet. So they want us to pick out an element from period 2, so that's what we need to focus on. Something that forms 3 single bonds. If it forms 3 single bonds, it means that needs 3 more electrons to complete octet. if it needs 3 more electrons, that means that it already has 5 valence electrons. If it has 5 valence electrons, that means this element is in group 5A. And if it is in group 5A, then it has, and period 2, then this atom has to be nitrogen. So let's see if our strategy works for the others as well. Forms 2 double bonds. 2 double bonds implies 4 bonds. 4 bonds implies 4 electrons needed. 4 electrons needed implies 4 valence electrons already present on the atom, which implies group 4A. So, period 2, group 4A is carbon. So, using the same strategy, forms 1 single bond and 1 double bond, meaning total of 3 bonds, 3 covalent bonds. If it's making 3 covalent bonds, needs 3 extra electrons. If it needs 3 extra electrons, means it already had 5. And if it already had 5, it belongs to group 5A, which brings us to nitrogen once again. Forms 2 single bonds and 1 double bond. This brings us to carbon again, following the exact same logic. So please remember, in this case, the number of covalent bonds that a non-metallic atom would make equals the number of electrons, number of extra electrons it needs to complete an octet. Okay, let's move on. Draw Lewis structures to illustrate the covalent bonding in the following polyatomic molecules. Now we are going to use a systematic procedure to draw Lewis structures. So, step number 1 for drawing Lewis structures is to count the total number of valence electrons for the molecule. Now, phosphorus has 5 valence electrons. Each of the chlorines has 7. So 3 of the chlorines will be 3 times 7. 21 plus 5 gives us 26. Gives us 26 valence electrons. Now the next step is we take the central atom, which oftentimes is the first atom listed. We take the central atom, write it out with its electron pair, with its valence electrons. Write out the peripheral atoms, or the atoms that surround the central atom, and denote their valence electrons as well. 7 for each of the chlorines. Oh, hold on. I apologize. That was my mistake. That's not the systematic name, systematic drawing of Lewis structures. Let's start over. I apologize. After counting the 26 valence electrons, we write the central atom, which is often the first listed atom, and then connect that with each of the atoms that surrounds this central atom with a single bond. So just using a single bond. Now remember that each single bond is 2 electrons. In other words, by doing so, we have used up 6 electrons off the 26. So if I've used 6 electrons off the 26 valence electrons available, I'm left with 20. The next step in the procedure is to fill up the octets of the peripheral atoms with the remaining electrons. So I have 20 left. I can use those to fill up octets of each of the 3 chlorines. Remember, they need 6 more because 2 electrons are already there in each of the covalent bonds. So now all the chlorines are happy, their octets are satisfied. Now let's figure out how many, let's count the electrons and see how many we've used and hence how many are left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 pairs, meaning 24 electrons. So I'm still left with 2 electrons, 2 electrons out of the 26 valence electrons. If you are left with any more valence electrons, those then go on the central atom. And now in doing so, phosphorus has also completed its octet, and therefore this structure is correct. Let's do the same procedure for OF2. Once again, count the number of valence electrons. Oxygen has 6 plus 2 times 7 for 2 fluorines gives us 14 plus 6, 20. So we have 20 electrons to play with in this case. Next step, central atom, which once again, oxygen, connect the central atom to the peripheral atoms, as many as there are, using single bonds only. So I've used up 4 electrons of the 20, left with 16. Use those to fill up octets of the outer atoms first. So we filled up for fluorines. And now I've used 1, 2, 3, 4, 5, 6, 7, 8. 8 pairs, meaning 16 electrons. I'm left with 20 minus 16 electrons, in other words 4 electrons, and then I can put those on the central atom to fill up its valence electrons. Its octet. As a final check, it's always a good idea to make sure that you have used up as many valence electrons as were available. So we had originally had 20 valence electrons. So if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we have used up all of the 20 valence electrons. Your structure cannot show less or more than the electrons that you have available to play with. Okay, let's go on. More of the same thing, but in this case they are specifying the simplest molecular compound to be formed with these elements. Now here what is important to realize is sulfur is in group 6A, therefore sulfur needs to make 2 covalent bonds. Fluorine is in group 7A, only needs to make 1 covalent bond. So in what ratio should we combine these so both sulfur and fluorine can be happy? Yes, so we will need 2 of fluorines to combine with 1 sulfur so that fluorine and sulfur can then have octets and be satisfied. Nitrogen, once again, same analysis. Nitrogen needs to make 3 bonds, and bromine needs to only make 1 covalent bond. So we would need 3 bromines to combine with 1 nitrogen so that every element can have an octet. So nitrogen in the middle because it's the one that's making most number of bonds, and bromines all around it. And then, oh, that's a Br, not a B. And then fill up the octets so that each atom is then stable. Okay. Now here's a little bit more involved a problem. We have to draw a Lewis structure but for these substances, but they've given us some criteria. C2H3N, but the 2 carbon atoms are bonded to each other, and one of the carbon atom has a nitrogen attached to it, and the other carbon has 3 hydrogen atoms bonded to it. Now, it's not stable the way it is because all carbons need to have 4 bonds and all nitrogens need to have 3 bonds. The first carbon, in this case, this one right here, does have 4 bonds. It's okay. However, didn't mean to do that. However, the second carbon is not done yet, nor is nitrogen. So what's the best way for us to complete their octets? So that would be the structure. Now, C3H4, once again, the criteria is a central carbon atom has 2 other carbon atoms bonded to it. One of the non-central carbon atom also has 1 hydrogen atom bonded to it, and the other one has 3 hydrogen atoms bonded to it. There are no more atoms to play around with. So, how do we best make sense out of it? if you put a triple bond right there, every carbon has 4 bonds and every hydrogen has 1 bond to it. Okay, so very quickly, now we're talking about polyatomic ions and not just molecules. Now, when you're doing polyatomic ions, the trick is that when you are counting the number of valence electrons, you must add for negative charges and you must minus electrons for positive charges. So, in this case, oxygen has 6, hydrogen has 1, but there is also a negative charge. So, for that one negative charge, you must add this electron, which gives us a total of 8 electrons. Everything else after that is the same. In other words, oxygen connected to hydrogen. We've used up 2 electrons, 6 left. Hydrogen does not need any extra. It can only take 2, can have only 2. Oxygen, however, did need 6 more, and here is the structure. Same thing, aluminum. Aluminum has 3 valence electrons, and chlorine, each of the chlorines has 7. So, I can't do my math today. 7. But then, because of the negative charge, you will add 1 more electron. So, 28 plus 4, we have in this case 32 electrons to play with. Aluminum in the middle, connected to the 4 chlorines. And then we've used up 8 electrons of 32, which leaves us with 24. Let's fill up the valence of the peripheral atoms first using those remaining electrons. And we realize we've used up all of the 32 electrons, and the charge must be shown outside of the parentheses. I added an ammonium ion just to show what to do in case there's a positive charge. So once again, we added an electron for a negative charge. In the same manner, we must take away an electron for a positive charge. So count our electrons, 5 from nitrogen, 1 each from 4 hydrogens, and this time we will take away an electron because of the positive charge. So the total number of valence electrons now would be 5 plus 4, 9, minus take away 1 gives us 8 electrons. Central atom, nitrogen in the middle, connected to the 4 peripheral hydrogen atoms. How many electrons have we used up? Exactly, all of them. So we are done. Do not forget to write the positive or the negative charge outside of the brackets for these ions. So the process doesn't change when you're dealing with polyatomic ions. The only difference is that you add electrons for negative charges and you take away electrons for positive charges. Okay. Here we are being asked to draw a Lewis structure for ionic compounds that have polyatomic ions. So the important thing here is to realize that the connection between the metal and the polyatomic ion is not a covalent bond, it's an ionic bond. Sodium from previous chapter, I hope you remember, sodium would have a charge of +1. So we are now left to figure out the Lewis dot structure for cyanide ion. Cyanide ion is Cn-1. Count electrons, carbon brings in 4, nitrogen 5, and then we add 1 for the negative charge. This gives us a total of 10 electrons. So the cyanide ion has carbon connected to nitrogen, and then if you fill up nitrogen and carbon, now we've used up all 10. However, we don't have an octet for carbon. So what do we do in this case? Yes, we move one of the non-bonded pairs on the peripheral atom, move it as a multiple bond. But in this case, we will have to do it one more time so that cyanide actually has a triple bond between nitrogen and carbon, and then each of those has a lone pair as well. And there is a negative charge for that ion. So when you're writing the Lewis structure for this compound, you must write it as where the ionic connection is very clearly shown. Let's do that for the last one. Once again, same idea. I'm very quickly going to finish this. There are 3 potassium ions this time, not just 1. And phosphate is P. Going through exactly the same process with a 3- charge.